Let us start our discussion with Newton's laws of motion with this first scenario. Suppose that you are driving in a car with no seatbelt on, and you stop suddenly. Well, what happens if you stop suddenly? If you're driving in your car, you're going to the right, and you're driving in your car, and you stop suddenly. What's going to happen is your body's going to stay in motion and move forward. And that's Newton's first law. It tells us that if no net force acts on an object, it maintains its state of rest or its constant speed in a straight line. And really, if you ever travel to, say, like down in Toronto and you ever have to take the subway and the subway stops, what happens to our body as the subway is stopping? Our body's lurching forward. That's the property of inertia. That is Newton's first law, that we will continue moving if there's no net force acting on us. Second law. When an unbalanced net external force acts on an object, the object accelerates. And that is Newton's second law. And we should just note or keep in mind that acceleration is in the same direction as the net force that is acting on the object. And this brings us to our most important equation for this whole unit, and that is the fact that our net force, F net, is equal to the mass multiplied by our acceleration. Third law. Third law tells us for every action force, there is an equal but opposite reaction force. Meaning if we push against the wall is going to give us a reaction force directly back towards us. And remember, for any type of Newton law type question, if we're ever having to solve a problem, Remember that it's always good to start off with our free body diagrams because it helps visualize the forces acting on an object. And just some notation, remember, FA is going to represent our applied force. We'll use FG for gravity, or the force of gravity. Fn will be our upward supporting force. Otherwise known as our normal. And we could have FF representing our frictional force. And those can all appear in our free body diagrams. So let us start off with our first example that we have. And this is a case where we have a child's wagon experiencing a frictional force of 73 newtons. Whenever it is in motion, that's regardless of the load that it is carrying. A horizontal force of 129 newtons is applied to the wagon, causing it to accelerate at a rate of 5.0 meters per second. In part A, we will determine the mass of the wagon, and in part B, we'll determine the force that must be applied to accelerate the wagon 7.5 meters per second squared. And the best bet always, let's just call the direction right as positive, and let us draw our free body diagram. In this case, since we have acceleration moving to the right and to the left, we do have the force of gravity that is acting on our child's wagon, but we have the normal force that's acting with equal magnitude, opposite in direction. We have some applied force in this case. Our force of applied is 129 newtons, and we have a frictional force acting in the opposite direction of 73 newtons. And for this case, we know that our net force will be equal to our force applied, subtract our force of friction since it's acting in the opposite direction. And from Newton's second law, this will be equal to mass multiplied by the acceleration. So this comes from Newton's second law. Since I have that force applied minus my force of friction is equal to mass times acceleration, don't worry about the net force anymore. Let's go to calculate now. So FA minus FF is mass times acceleration, and we're looking to calculate the mass. So the mass, simple solving equation, we'll subtract our force applied and our force of friction and divide by our acceleration in this case. So therefore, we'll take 129, we will subtract 73, and divide by our acceleration of 5.0. Which is 11. So therefore, the mass of the wagon is 11 kilograms. And remember that our SI units for mass is 11 kilograms. Now let us look at part B, where we're determining the force that must be applied to accelerate the wagon 7.5 meters per second squared. Remembering the mass of our wagon is 11 kilograms. So just recall that free body diagram yet again. Force of gravity, normal force, we have an applied force, which we don't know, and we have our force of friction, which was always 73 newtons. We have our mass of our wagon, which is 11 kilograms, and we have our acceleration of 7.5 meters per second squared. So Newton's second law tells us that our net force is equal to the sum of the forces acting on the wagon in this case. So Fa minus Ff, and that will be equal to our mass multiplied by the acceleration. We're looking to solve for our force applied. I have this equation here. Don't worry about the net force. I just like to write it out, show our sum of our forces. So this is going to be our force applied will be equal to our mass multiplied by our acceleration added the force of friction. So that's going to be 11 times 7.5 add on 73 newtons. So that's 82.5 plus 73, and that will be, quick mental math in my head right now, 155.5 newtons. This question asked for two significant digits. Therefore, the applied force was 160 newtons, and this we're going to assume, because of our diagram, was to the right. So free body diagrams will always help us determine what forces are acting on the object, even in two-dimensional type problems. This was a one-dimensional problem. Let's see a two-dimensional problem in which a barge is pulled through a canal by two horses, and the ropes make an angle of 40 degrees with the horizontal, and there's two horses on each side of the canal, and they pull with a force of 5,000 newtons. Determine the frictional force applied by the water as the barge moves at a constant speed. And remember, constant speed means that our net force must be equal to 0. So let us see what we would actually have in this case. We have our barge, which is going to experience some type of frictional force opposing the motion of the horses pulling at a 40-degree angle with the horizontal. Of 5,000 newtons by each horse. And if you will just assume, we see that we have one force acting in the negative y direction here, and we have one acting in the positive y direction. That means that both the vertical forces are actually going to cancel out in this case. If we were to calculate it, we would get opposing forces. However, acting in the positive direction, we see that our force in the x direction is actually going to be the same for each horse. So we can assume in this case that our force is going to be 2 times 5,000 cosine of 40 degrees. So that means that would give us 7,660.4 newtons, and that would assume that this is in the right direction, and that was in fact the same as our force applied by the two horses. So pretty much what we have is this: an applied force of 7,660.4 newtons and a frictional force acting in the opposite direction. So that tells me that our net force, which will be my force applied minus my frictional force, and because it's a constant speed is 0, that means the force applied and my frictional force must be of equal magnitude but opposite in direction. Therefore, my frictional force is negative 7,660.4. So therefore, the frictional force, or the force applied by the water, is, because this has to be one significant digit, 8,000 newtons, let's say left, because we're operating in the opposite direction. And I hope that helps for some of Newton's problems in one dimension and in two dimensions.